Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Thank you for joining the GeoScience and GeoEnergy webinar of 3rd of December 2020. We are approaching the end of the year as we proceed with this webinar series too. Sebastian and myself are grateful to you all to keep the momentum, connect with us every week for 1 hour scientific gathering, and we are pleased and delighted to see that the channel has 1,600 subscribers, and that's really encouraging for us to keep the momentum also high. As we get closer to the end of the year, Sebastian and I have designed a plan to feature you all for 10 seconds. You need to create a 10 seconds message to your colleagues, friends, and global scientific community with the right environment you like to be. Tell a little bit about yourself, who you are, where you come from, what did you like the most here, and wish everybody a good and pleasant year. We are going to collect them all, assemble them together in one video, and release it in our channel in 2 weeks' time. And then everybody can be featured in this channel. So it's your channel at the end of the day, and we would be pleased and delighted to see who you are and where you are from and why you are here with us, and all these kind of online events that we are having in this year. And also, I would like to also mention about the Tea Time Talk series. We have been mentioning it every week to motivate junior researchers to connect with our colleagues at a Tea Time Talk series to present your PhD work, postdoc work. If you have done also an exciting master thesis work, also present, let the community get strong and build up together your network. So about the lecture of today, you've seen we have addressed different topics so far in our channel, from modeling, from vision, from the company side, from national labs or scientific or research centers. And we are today and next week are getting to the depth of geology, the heart of the geosciences. So Sebastian and myself are delighted and pleased to welcome Professor Giovanni Bertotti from TU Delft, my own colleague in our own department, as the keynote speaker of our webinar today. Giovanni is Professor of Applied Geology at the Department of Geoscience and Engineering and chair of the section called Applied Geology 2. He received his master's and PhD degrees both in Earth Sciences, a master's from University of Pisa in Italy, where he originally comes from, and ETH Zurich for his PhD, where actually coincidentally Sebastian, myself, and Giovanni all hold our PhD from ETH. So that's just an occasion, the different departments, but from the same school. He then joined Vrije Universiteit Amsterdam, University of Amsterdam, first as assistant and then associate professor. He worked on strengthening field geological research and its integration, especially with lithosphere scale basin modeling studies. He continued his position there for about 23 years. In 2010, he became part-time professor at TU Delft, and finally in 2015, we were lucky enough to have him as full professor full-time at TU Delft. Giovanni is a structural geologist with a long experience in the analysis of multi-scale deformation patterns in different tectonic settings in different parts of the world. Building on his vast expertise on evolution of sedimentary formations, he has led research and education towards more quantitative descriptions addressing the stress and strain evolution of rocks during basin formation and deformation. He has established research on naturally fractured reservoirs, combining numerical modeling techniques with observations from outcrops, analogs of buried reservoirs. For you all, if you don't know, he has his own drones, by the way, folks, and just takes photo from the outcrops. It's so fascinating what he does. He has worked on fractures networks in a variety of lithologies, from fluvial deposits in Jordan to turbidite sands in the Karoo Basin of South Africa, as well as on tight, shallow water Devonian sand in Morocco. He also studies fracture patterns in sub-horizontal and in folded shallow water carbonates on the basis of outcropping analogs in Tunisia and Brazil, building on the strong collaboration with geomechanics and flow modelers at TU Delft and elsewhere. I believe Sebastian also and Giovanni have been also collaborating for some time. He leads research and education on quantitative geology by integrating characterization and modeling. So that's quite a very impactful study and research and contribution in the scientific community has. I myself and my group, and I believe many people are fan of his characterized fracture networks, and we use them in our research and modeling side as well. It's a pleasure and honor to host you, Giovanni. We are dear colleagues, but still it's really our pleasure that you accepted to give this lecture to the audience. Please note his lecture will last for about half an hour and then followed by questions. Like always, please type in your questions. Sebastian would chair the discussion session afterwards. Without any further ado, the stage bandwidth, everything is all yours. Giovanni, please go ahead.
Thank you very much. Hadi and Sebastian, it's really a pleasure. And we've been collaborating and helping each other quite some time. So it's really have really good memories. And also with Hadi, we are continuing. So it's an honor. It's a bit of a challenge to be one of the geologists in this community. But I'm kind of used to this challenge because here we are in Delft, we are really together with engineers. So the struggle between geologists and engineers is our daily bread, but it's extremely productive one. And in this perspective, what I want to do is really to give you a bit the geologist perspective to this issue of flow through basins, and especially to the hypogenic karst development, which have been becoming quite important in the last years. This is what we are talking about, and the subsurface in several places people have found. Is there? Let me see my pointer.
Yeah, we see your pointer. Yeah,
this is better. So in several places they've come out to these caves. And this has been the subsalt of Brazil, but also here the Paleozoic carbonates, which are targeted now for hydrothermal research, have similar issues. And it's obviously these on one side, they provide large permeability, on the other side are engineering challenges. And in any case, we would like to be able to understand where they are and eventually to be able to introduce them in flow models and mechanical models, or in any case, reservoir models. So that's our goal here. The goal is really to predict, to develop rules and workflows somehow to predict where they are, how big they are, what are their structure, and so on. That's my perspective in this. And to do this, I will obviously take a geological approach. I will make a story. And this story will include the different components, will include fieldwork, obviously, from various shallow water carbonates in different basins, different parts of the world. We will use these digital cave models. These are not done with a drone, but with a LiDAR. And then we'll be including also numerical modeling work of the DARTS community, which is then, obviously this is not my strength to put in a diplomatic way, but I have a support by Stefan de Hoop and Denis Foskov. Now, this is the one. This is a side section across the central part of Brazil, and it kind of represents one of the possible settings where we have these hypogenic dissolution caves. Hypogenic dissolution caves means these caves where the source of the chemical aggressivity, CO2, H2S, comes from below. Can come with most of the fluids, but not necessarily can result from the mixture. So this is basically a 4D basin. On the left-hand side, there will be the belt, and here you see the 4D basin becoming shallower and thinner towards the right-hand side. So these are the components of my story here. I'm interested to look a bit what kind of fluids do we have at the beginning of the story, and what is their motor, why they start moving. Then I'm interested to see all this long travel they do along layers, along layer parallel flow, and then we will see that at a certain moment these are captured by steep fractures, and then the layer parallel flow transforms in upper movement, and then somewhere in some place we'll start getting our hypogenic karsts. So these are the four components of my story. on the whole, I must say that there is really very, very little, at least to my knowledge, and I hope somebody will tell me that there is a lot, much more than I know. There's very little work on the entire system. Somehow the large-scale modeling work, which used to be done in the past, is not really fashionable anymore. So this is also an encouragement to do things. This is why I had to go back to some really very nice pioneering work by Mr. Garvin. And he was saying on one side that there is one possibility to get these movements of these fluids is over in the Forty Basin. This is similar to the one which I was showing before. And this is essentially the formation waters, which are then buried by thrusting. And so there is a tectonic load, and these start moving because of this tectonic load. But there's a study, a couple of studies which have been done recently in a group of Manchester, with Kathy Hollis and so on, that in a different setting that say that in order to create the extensive dolomitization, which we think is associated with these fluids, you need much more fluids than available in the formation water. So there you see that when we start doing things in a quantity manner, things can get less obvious and less intuitive than they look like. The other, and this is not exclusive to this, the other component which you can have is that you can, if you have exhumation, or if in any case you develop a high topography fold and thrust belt, a mountain belt, then you can have waters coming, initially meteoric waters going into the system, and then start being warmed up here in the deep part of the basin, then start moving, driven essentially by hydraulic head related to this mountain belt. So this is also, for instance, the case of Brazil, which I will talk about. It was a Jurassic exhumation event, and this is one of the best way to get a high topography, which translates then a hydraulic head which moves. According to Garvin, the layer parallel flow is fast enough to keep a thermal anomaly, and this is obviously an important part of the story. So they need to be fast enough in order to carry the temperatures which you expect to have deep in the basin, to bring them somehow to keep your fluids hot enough. This seems to be the case. So this is something which is not really worrying us too much. So now, how does this flow occur here along the layer parallel part here? Now, this must be related to fracture. This is my assumption here, that is only if you have distributed fractures, then you have enough permeability to have this flow fast enough. And the distributed fracture is really referring to fractures which are not related to faults, which are not related to faults, what we call the background fractures. And this is something which is, unfortunately, is really not attracting enough attention. And a lot of people are working on fractures related to faults. And I think we need to do more on the background fractures. So what do these fractures look like? This is my attempt here, is try to see a bit how do we predict these things and how do we model these things. Now, the normal approach is that you have a borehole, and in this plot you see from a borehole, see these points. This will be from a stereo plot, and you see that in fact they are quite scattered. So somehow, in a reason, and I don't know exactly how this works, but you have from wells you have quite a chaotic picture. And then obviously the models don't like this, and they start simplifying the picture, defining some sets which obviously create to me a lot of stomach pain, because this is really, might be statistically sound, but it's geologically not very sound, and started forgetting the dip, for instance. So you get some sets and things get kind of simplified. And then the people, they use the various tools to derive some DFNs. And then they apply some aperture and stress field, you get your flow models. Now, if you look at this in the middle here, this is, for me, is geology is not a nice network. It's really what I call an ugly network, in the sense that it is quite different from what you see in reality when you use the same scale, the appropriate scale of observation. So that's a bit of a problem here. So the other option which we have to populate our model is to, in theory, to use some rules here. Now, the landscape of rules is a bit of a dramatic one, in the sense that we don't have rules to predict if we get mode 1 or mode 2 fractures. We don't have good rules to constrain length, spacing, distance, and so on. And we don't have good rules to predict the Butman relationship. So when the people are desperate, what do? They go in outcrops. And now let's see what we find in outcrops. First of all, there is not enough study done at the right scale. So this is a picture you see to the right. You see the scale is 100 meters. This is the scale where you have to work on. It doesn't really help if you look too much at the small scales. But if you look, you need to be able to look at fractures which develop during subsyn and not during exhumation and so on. And our criteria to do this is that basically we look only at fractures and fracture networks which have been overprinted by layer parallel stylolytes. Layer parallel stylolytes are dissolution features which develop parallel to the bedding, which we think are formed during overburden, during burial, and therefore the fractures which formed before this are fractures which are really relevant to our study. If you look at this picture here, you already get the kind of idea that things are very well organized. There is a set like this, there's another like this, and there is a couple of fractures like this. So you see that seems that nature is really doing a better job than what we see from a borehole that is much more chaotic. Just the two other pictures which I show you what I'm talking about. This is one type of a common feature what we see. This is really a much smaller scale, but we see a larger scale. You see two sets of fractures. And then here there is another discontinuity, but in fact it's a stylolite. And all of these things, this is the outcrop seen from the side. So these are my bedding parallel stylolites. And you see that most of the veins here, they stop at the stylolite. So we're looking at these features here. These are the criteria, these are the network which we look at. And you see in thin section, this is my stylolite. And you see that a lot of these, all these veins, in fact, that they form before the stylolite. So this is something which formed during burial, and these are then the kind of fracture we expect to see in these layer, playing an important role in the layer parallel picture. This is a bigger one. So see, this is the picture of these carbonates. And when you start looking in more detail, you see these, for instance, this discontinuity here. This is a vein, and this is also a vein, and this has a strike slip component. So you see, you start putting together a number of elements, this direction with this direction, and they kind of belong to the same system. And that's an important thing. What we realize more and more is that if you look at the kinematics of these things, you also see that they belong to the same unit. And again, you see these are my bedding parallel stylolites, and you see that they overprint the veins, and therefore all these things they form before, so during burial, before they reach the present day depth or the maximum depth here. So that's the conclusion, our conclusion from outcrops, that networks in reality, if you look large enough, they are simpler than what we expect in general from geologic history. So some of these platforms which I showed you had a complicated history, but somehow they absorb, they take the first stage of deformation, but then after this, they kind of blocked. Now, if you do a detailed analysis in looking not only at discontinuities, but looking also at the kinematics, then you can put different directions together. You can put, for instance, some fractures, you see that some fractures are mode 1, some fractures are mode 2, some fractures of discontinuity stylolites. And these are not three different independent units like you would model them if you do a normal DFN, but they belong together. And therefore, the idea is to start modeling not necessarily the loose sets, but blocks, building blocks, units, which are in fact composed of these three units. And the idea is that in this way, we can really simplify very much our populating our network and getting something which is more reasonable, and it's much more geologically controlled than if you just simplify, extrapolate stochastically, lose sets one from the other. In geologic terms, we see that there was really very often we see sets which are controlled by a tectonic stress, where there's tectonic, the sigma 1 is subhorizontal, and then depending a bit, sometimes you have a sigma 2, which is vertical, sometimes which is horizontal. Now let's go back a bit to the geology here, and I show you here what these things look like. In the Heriot-Watt basin, we have, like in many places, two different aquifers. We have a quartzite at the bottom, then there is some tillites, some shales which separate from the upper aquifer, which is made of carbonates. And this is what you see in the carbonate. These carbonates around the cave we've been working, they're all dolomitized. So this is really the indication that there's fluid, there's flow, a lot of magnesium-rich magnesium-rich fluids, which have been traveling all along this basin, along the layer parallel part of the path, being loaded in magnesium, which is then deposited here. And it also, you see that there is some, we call them tension gases. These are small systems of veins, which don't contribute very much to the permeability of the rock because they're fairly small, but they're filled with dolomite. So you see that they indicate that these features are active during the flow of in this lime carbonate aquifer. A certain moment here, this is then these layer parallel flow. A certain moment, these fluids are intercepted, are kidnapped by steep fractures. And this moment, things have to change because when they move upward, the danger of cooling is very high. And if you cool it, you stop. So that's really now a race where the upward movement must be very efficient in order to avoid cooling here. So we need really steep fractures. And these are either steep thrust or strike slip faults. And these are all both good candidates to allow for a rapid flow, upward flow of these fluids. This is a picture of one of these strike slip faults, and you see can have zones of very high permeability there. Once these flows, you see, this is the upward movement. Now, where is the karst now in here? This is my fluid moving upward. We get to the karst and these caves, the dissolution caves. When these fluids, a certain moment, they stop against an impermeable layer, just overlying a permeable layer. So when these fluids, a certain moment, their upward movement is blocked by a layer with low permeability, overlying a permeable layer, then they will start moving sidewards. And this is the moment when we start developing our dissolution. And this permeability, at least in the caves which we looked at, is essentially a fracture-related permeability. So these are the layers where we have the caves. And these are characterized by low spacing, which means high density. So the mechanics stratigraphy, the fracture stratigraphy, is the one controlling the development of these caves. Now let's see this flow starts moving laterally, and let's see what happens. This is my strike slip fault propagating upward, and at a certain moment this will cross the boundary between the two aquifers and allow the invasion of these fluids, which were first in the lower aquifer. They allow the invasion of these fluids in the upper aquifers. So we bring silica-rich fluids in the upper aquifer and the carbonates. So this is the SiO2-rich fluids which arrive. And this is what you get in the cave. Then this is the dolomitized bodies. But now suddenly you have big fractures, steep fractures. Some of them are filled, and at this time they're filled with quartz. So this is a very different situation than this dolomitized body where we had our dolomite-filled tension gases. So this is something which is made possible by the upward growth of the strike slip fault, which connects the two aquifers here. Then we have the speleogenesis. So this is the moment when we form the hole. And what is interesting in some of these caves, you see that the internal part of this cave is covered by a crust of silica, which according to the speleologists is quite rare. And this is interesting because we have at the same time the deposition of the silica and the dissolution of these carbonates. And this is related to the fact that when my fluid starts moving laterally, it decreases the temperature, and this increases the dissolution of the calcium carbonate, but decreases the dissolution of silica, which start precipitating. So the interplay between these two kind of dictates the general structure which you get in these caves. These caves, some of them look really a bit like this. So they have a main entrance, they have a main structure, and then they have some branches a bit to both sides, but other are extremely regular. We call them, or the speleologists call them mesas. And these are characterized by two sets of tunnels, of passages, and they are extremely regular. You see, they have a very regular spacing, and they have also very regular dimensions. This is what we want to look at on one side using digital models of caves, and then integrate this numerical models. We're interested to see why is it that we have this recurrent spacing. What is controlling this recurrent spacing? And what is the trade-off? Why do we have a kind of equilibrium width of these tunnels, which is something which we find all over these tunnels here? And the other issue is what is the impact of fracture on this? Because fractures, normally people think they're absolutely important, but nobody has really checked this in a quantitative manner. So let me quickly show you a bit what the results of these caves. These are caves, and then we measure a couple of them with a slider. And having a digital model of these caves, then we can do a lot of things. This is a section through these tunnels, and you see how amazingly regular these caves are, both in terms of spacing, but also in terms of dimension. Something very, and this is not obvious because you really have to think in terms of flow. You need to kind of progress dissolving at the same time in different tunnels, which is, again, it's not an obvious thing to do. If we look at these plots, they show in this cave here, the Lago de Bode cave, they have the width of this would be the northwest-southeast oriented tunnel system, and this would be the other tunnel system. And what you see is that these widths, they remain fairly constant over large distances. So there is an interesting trade-off between the forward movement of this dissolution of this tunnel and the sidewards. So that there must be a trade-off by which at a certain moment the tunnels don't grow anymore, and they are kind of similar for all the tunnels, and amazingly also for the other set, not only for one set, but for two sets. And this is, in terms of flow, it's something which is kind of counterintuitive, at least to me here. Now, people have done some wormhole experiments, and these are experiments which have been done in the 90s, and these were the hydrocarbon community that were acidizing their cores. And they did a number of really nice experiments. And what you see here, these are these analog experiments, the experiments in the lab. And they used to describe these different patterns. They describe the Peclet number, the damp current number. The Peclet number gives an indication of the rate at which the material is brought to the wall and removed from the wall where you have the reaction. And this is something with the damp current is to do with the reaction itself. And you see, you can get the white part is high porosity areas. And you can see in this case here, you get something which is very sharp wall. And this is the situation which you get in point number 1, where you have a really very high damp current number, so a very efficient reaction, but the Peclet number is very low, and therefore nothing is removed, and therefore the reaction does not improve. On the other side of the spectrum, you have this point here, which is characterized by high Peclet number and very low damp current number. You see that you get the dissolution everywhere and porosity everywhere. Funny enough, in the cases in between, here you get one main tunnel, but these here, you see that we start developing some tunnels or some passages or whatever, some wormholes with the kind of constant spacing. So this is something which seems to have an intrinsic value, something dictating that there is a regular spacing in these wormholes which are forming. And this is something which reminds not the maze in the sense of the two directional tunnels, but of one directional tunnel. And this was something which we want to see what is really dictating the spacing, what are the factors controlling the spacing. And note that here there is no fracture, so the fractures in this case are completely irrelevant. Now then, obviously, then Dennis and Stefan, I hope is a PhD who's doing most of the work. This is the DARSA simulator, and this is something where if you need some more information, you can ask Stefan, who is here. I think maybe also Dennis is here. And this is something which they've been developing, and I leave them to say how good they are. What is interesting for me is that there is chemistry involved in it. There is the dissolution part is in there. The flow part is there. We don't have yet the thermal mechanical coupling, so we don't have yet the decrease in temperature of the fluids when they move from one side to the other. And with the other thing that they are working on is to have the mechanical coupling. Let me quickly, I'm going here towards so a lot would say the model part with what I'm showing here is the role of fracture. This is the interesting thing because, and this is a kind of, was interesting because as I showed you before, those experiments in the lab created some regular spacing even without fracture. So what is really the fracture? And in the field or in the caves, we see that, for instance, there is many fractures also between tunnels. So it's not that each fracture corresponds to a tunnel. So what is really controlling this spacing? Are the fractures doing an important job there? Now, this first model has a very simple structure, has five fractures along the direction of flow, and they are straight and they go from one side to the other of the model. And in this case here, you see that if the permeability is high, then it's easy. And what you see is that basically all these fractures that are used at the same time, because it's so direct, the connection, that there is no reason to choose something different. And you see that there is some attempt also to use this fracture, but this is not developed yet. And the moment that the fraction becomes, the aperture becomes very low, then obviously we'll choose one and they are not present anymore. Now, this is really only the situation where you have extremely straight and extremely already open fractures, which allow you really, these are kind of already mini tunnels, which allow you for the flow. If you go to a more complex and more realistic situation where you see here, this is a fraction network generated, so this is not really a case study, but in fact, they are fairly well organized. There is dominant directions, and it's the same. And what you see here is from left to right, we decrease the fracture aperture here. So this is high and this is low. And here you get something the opposite effect, because if the fracture aperture is high, then the system finds immediately kind of backbone, and that's the one which will choose. So if the fracture per aperture is high, then you don't develop a maze, because among all these fractures, then it will use this, create this backbone, and this is where the flow will take place. And in fact, to create a maze, you have to eliminate the fractures, creating them, assigning to them a very, very low permeability. And then in this case, we started developing here something which reminds of these fractures. So there's apparently a kind of equilibrium trade-off. If the fractures are very open and very continuous, then these are immediately used. But otherwise, the system is going to choose one system rather and leaving all these other behind, therefore creating something like a backbone, a unique channel, so a big tunnel, rather than creating really a maze. Now oops, I'm kind of stuck. Okay, the last example which I want to show concerns here diffusivity. So the rate at which these ions are moved from high pressure, high gradients, high pressure areas to low pressure areas. This is the dissolution of CO3 in the carbonate rock. And you see what you have here, and we have decreasing coefficient. And you see that if things go very fast, if the coefficient is very high, then everything is dissolved. Whereas if it's slow enough, you see that all these, they started developing together. This is really something which is creating your maze. So this is another component here, which we want to further investigate and to see how much this network, existing network, dictates the enlargement, and how, if we do reach kind of equilibrium in the width of these tunnels here. Now, this is basically my presentation here, and I want to just this to the right is really, I think, one of the nicest one of these caves, where you see that the water is extremely clear. It means that this is the water table, but it's something which is really, there's no influence from the outside world. This is why it's extremely clear. But what you see, these things, this is the pile of calcite flakes, and they are related to the fact that you see that if you go down here, there is a shaft, there is a fracture from which there is CO2 coming up, bubbles of CO2, and this is the hypogenic component. And when they arrive to the surface, they make this kind of calcite sand. And this is my hypogenic caves here. Now, our conclusion for this is that I think it's really, we need to go towards a comprehensive model of the entire system, because a lot of things will be decided on the basis of how much water do we need. Is there the hydrogeologic motor is efficient enough to have these quantities going through there, dissolving and precipitating? I think the layer parallel flow occurs along these distributed fraction networks, which, if we want to be able to predict them or to model them, we need to simplify. This is the typical fight, so to speak, between the geologists and engineers. Engineers or the modelers, they work to be able to implement more and more fraction of the model. What I say is that we don't know these fractures. So my attempt is to simplify the reality in order to find a good, then we will find a good compromise between us. The cave they develop when the upward movement of these fluids is deflected by the impermeable layers, and that's the moment when things start really dissolving. And I think that in general, the role of fracture is less obvious, and then we should really investigate if there's a kind of intrinsic regularity in the system, the chemical system, by which you get these nice spacing here. And I think what we are trying to do, I was mentioning these old experiments with Peclet number and the Damkler number and so on. What we are trying to do is really, can we translate these dimensional numbers or these patterns in hydrogeological scenario, in the sense of how much water do we need, how fast does it have to do, what are the chemical characteristics, what the aggressivity of these fluids in order to really to kind of apply these models to the reality. This is what I wanted to say. I thank all of you. I thank all the people who have been working with me in these interesting studies, which has been really interesting to do. And I look forward now to questions.
Thank you very much.
Okay. Thank you very much, Sebastian. You are most welcome. Please, the session is open for questions until you are typing your questions. Sebastian may start to engage with Giovanni, and then we will address the questions. Sebastian, please.
So thank you very much, Giovanni, for a great talk, and it brings me back to discussions we had what seems an eternity ago in Brazil, the kind of research that we could do in this field together. So it's great to see this coming along. Before we start taking questions, and please do enter your questions in the chat room for Q&A. Hadi reminded me you're recruiting currently an assistant or associate professor to your group, or to Delft, to work on fractured reservoirs. Hopefully this is inspiring a lot of people here to talk to join you. So maybe you want to take 1 minute or so to tell us what you're looking for.
Okay. Okay, what we're looking for is somebody who's really, really clever, very good, socially also a nice person. But what we want to, there's 2 lines which I think are important for us. We want somebody who has experience with outcrops. We, in the entire department, we still think that outcrops have an important value, surely in terms of teaching. So we need somebody who has a geological background. On the other side, we're going towards more and more geomechanics. So we need also somebody who has to have some geomechanic knowledge, but I would say geomechanic knowledge not only in the lab, because we're interested in knowing geomechanic property at the scale, at the appropriate scale, which is the tens of meters to hundreds of meters. So the ideal combination is somebody who is really able to combine these 2 fields. Deadline is 20th of December.
Okay, so there's a nice Christmas present for everyone.
And it can be open, it's open, the entry is both at assistant professor level or associate professor level, depending on the level of expertise and CV.
Great, thank you. So let's go to the questions. I do have some myself, but I take them from the audience first. So we start with Musa. Thank you for the nice talk. How do you decide what properties the fractures have, specifically at the barriers? Are you deactivating them? From you
the numerical model, you mean?
Yes, from the modeling point.
Yeah, and this is Stefan's work. Stefan, what are you?
I think, at least from the geological side, Giovanni, how do we characterize these fractures and assign them some property? Maybe you can just, as a geologist, enlighten on that subject.
Yeah, the problem is that what I see in the cave, I see either, this is part of the issue. This is really part of the issue. The fractures which we see are very thin. And usually these are veins. So in a way, they really it's not really exist. This is what brought us already from me at least at the beginning to the idea that the role of fractures are kind of overestimated, because at the beginning these are very thin, they're very they're veins, so they're filled, and there is many of those, and somehow once every 20 or 50 is chosen, and then you start to enlarge. But you have to really see that at the beginning, this wall is fairly homogeneous. So the question is really, why do we start to dissolve in one part, and in the maze we progress at the same time with all these fractures, which is very different from the simple model which I was showing at the beginning. That model does not exist, because you don't have a situation where you have really continuous pipes, which you only simply have to enlarge. So that's really the difficulty, is really to start. And I think this is why we think is really what is controlling the initial kind of spacing of these wormholes. And then you need to have a fairly close fracture and a lot of discharge. So the work which has been done by other in analytical terms, so you see that if your discharge is very high, then you can really create a situation where while all the irregularities keep growing at the same rate.
But Sebastian, you are the chair now. If I'm allowed to just
you're allowed to ask a question.
But with the model part, you get input, and that's we just simply populate the properties there, and we would wish to populate them most meaningfully, so that when a geologist look at it and say that makes sense really. I can deactivate a fracture and say it's not there. I can make it a barrier, or I can make it, conductive. If you look at my characterized fracture, I could do purely geostatistics. I could do meaningfully like a stress distribution based or so. What would be your advice to make it more meaningful?
Yeah, we use usually these. I think I don't hear you anymore.
I am not speaking.
Okay. Okay. There is a bit of delay in what I see is a bit.
Yes. That YouTube link has about 20-second delay. Yeah.
Now, this situation, these are veins, so they have a zero aperture effect. It's only the moment if you put them under stress, they start getting open a bit. That's the situation. For the rest of the fractures, clearly the relationship that people sometimes use with length is something which doesn't work, because you get really very, very high. For the length which we see, you get very open fracture, which is something which you don't see. So we usually use a bit of these, modify the stress dependency, a bit of this Barton-Madness approach. This is the kind of thing. So you get a bit of reasonable values, but it's 2 millimeters.
Thanks, Sebastian, for letting me squeeze my question.
I'm going to be sneaky and I just continue asking a question myself here. I know there are lots of other questions. I'm just itching to ask that question. So looking back at the great work that Kevin Bistam has done on looking at fracture apertures, Giovanni, have you looked in your models on the cave formation of how the different aperture models influence the formation of the karsts?
Sorry, I missed the question there.
So Kevin Bistam has done a really nice PhD with you, Giovanni, where he looked at how different models for estimating fracture apertures, and with that fracture permeabilities influence fluid flow. So have you looked at how karst formation would change if it? Not yet. Okay.
Not yet. That network which was shown is generated, so it's not a real network. But this next step is what we're doing is really taking a real network and then start seeing what happens there.
Okay, great. So let's go back to our audience here and see that Stefan is also answering some of the questions. Thank you very much for that, Stefan. But Mariana asked a question. Thank you for your talk. How do you decide the volume or area of the system to create the simulations? Can you say something about the representative equivalent volume?
All the modeling work. This is not my... So the question, thank you for your talk. How do you decide the volume area of the system? At least my reading of these experiments is really to try to test a bit some ideas, because that's what I'm doing here, and it's still far from developing a really specific situation. For me, as I said, the interesting thing which I was observing is try to see this regular spacing, which I think it's not controlled by fractures. So that's something which we're trying to explore. And the second is to see if how do we get these really quite amazing constant widths and heights. And these shapes of these tunnels is fairly constant. This is what the kind of, in the qualitative base, this is what I'm trying to understand here. Okay. At least that's my perspective.
So moving away from the modeling questions, and Maren, one of our former speakers, has 2 questions. The first one is, again, thank you for the great talk. I wonder which role do fractures compared to the caves mazes have when we produce water from these layers? Any thoughts on that?
I wonder which role do fractures compared to cave mazes have when we produce what? I don't understand very well. I wonder which role do fractures compared to caves have?
So the caves are more important for production, or the fractures?
The caves are obviously the most important component. Say when you develop these caves, when the caves are there, then the fractures don't play any role anymore.
But then you drain the caves quite quickly, and then the fractures connect you up to the different.
Yeah, I think the dimension, the volumes are so different that in fact it's. I think that the fracture part is important for the lower part of the system before you start developing your dissolution caves.
And Maren has a follow-up question where she wonders what would change, or are there any changes if you were to produce from different layers and mix fluids?
Yes, I think that's surely an issue, but we have not looked at the production side. I think this is something which we started to look with a master's student. I think when you start producing that, you have really also big problems of mechanic stability there, right? If you decrease the pressure there. So that's what some work that you try to do is how far these things are stable when you are at 4 or 5, 6 kilometers depth. And they are, if they're empty, they're clearly not stable. So you need to fill them either with breccias and or with some kind of fluids. And then obviously in the moment you start producing, then you might have really important mechanical issues.
Thank you. We have 2 questions from Nino Kilona. Again, thanking you for the nice talk. Lots of things to think about. What is the role of flow rate and host rock permeability in this project? So you look at permeability of the rock matrix. Does that change the evolution?
I think that those experiments which you showed there, well, in the reality, yeah, it's always very difficult. The rocks which we've been looking at there don't have a really high permeability, but they do have something because the dolomitization affects really large body of rock. So that means that there is some flow also in the rock itself. And in that part, as I said, there is the most probably is by this combination of fractures and matrix. When the models themselves, they have some permeability, but Stefan is more able to tell what the relation between the two there.
Okay. Because Nino comments and says, from his experience, I would expect that the interplay between rock permeability and flow rate should also be controlling how important the fractures are. What do you think? What are your thoughts on that?
Yeah, there's a relationship. Yeah, the relationship is there. That's clear. And this especially for what we are called the last diagram where you have this diffusivity. You see that if on the other side you have a high permeability of the rock, then you invade the rock immediately, so you localize less. But in the tunnels there, this is really localized dissolution. It's not that you have many small tunnels in between them. There is only those ones in the maze or outside, but then for the rest there is really not much.
Okay. I'm afraid we do have another question for you on the modeling, Giovanni.
That's at the end. I will never do this again.
No. You should actually enlighten the numerical modelers as a geologist.
So Youssef, again, thanks you for your presentation. From a numerical modeling perspective, are there any studies? Have any studies been done to focus on the influence of the fracture network? So comparison of high versus low density fractures. Are you aware of anything there?
Don't focus on the influence of fracture network on what?
I assume on the evolution of the caves, the karsts.
Never done in a quantitative manner. This has always been something which I mean, after many years of coexistence with engineers, I know that some things will look intuitive. If you go them on the quantitative side, then they are not so obvious anymore. And that's exactly the discussion. My observation was that often you see the directions are there of these fractures, but there's many fractures which are not picked, so are not taken. So the spacing of the fractures might be 1 meter, for instance, but then the tunnels are 10 meters. And then why is it 10 meters? Why they decide to pick only the 10th and not the 11th and so on? So that's these things were kind of obvious. And this is why we started looking at all the literature and trying to see with the model if we develop a regular spacing also in the absence of fracture. And that's the case. Now that's a much smaller scale, so we have to see if it's applicable. But this is exactly, I think that work which I was mentioning, Golfier doing in dimensional numbers can be really interesting because dimensional number you can try to see to give them a geologic reality, a hydrogeological reality. And then things can get really interesting, I think.
So just should point out that Stefan is really busy helping you to answer questions as well in the chat room. We do have a question from Lu Yuang, and similar to a question that I had. Again, thank you for the great talk. For 3D geological formation, how do you determine the parameters in the field, especially if you want to transfer the data from a 2D computer model, which may hide some key features? And that's a question I also had. So are there, in the models that we're running at the moment in 2D, are we missing part of the story that allows us to understand the formation of the caves, of the mazes in the 3D world?
I don't think that I don't think that's the worst thing. I don't think that's the biggest, the bottleneck. I think that most of the flow along the layers, you can see it more or less in 2D. It's a bit 2.5D through a layer. And also to the side in the upper part where you get the karsts to develop, it's not very thick, maybe, I don't know, a couple of tens of meters, but it's not hundreds of meters. And I think that they are making an assumption that things don't change in these 20 or 30 meters. It's not a horrible assumption. Let's put it this way.
Okay.
That's not my biggest worry. So on. Also, yeah, that's not the biggest worry I have.
If you were to speculate, Giovanni, and I know that's part of the modeling work and part of the analysis is early on. And well, you're starting sort of on that journey. Do you expect to see sort of tipping points in the behavior, let's say above a certain connectivity, similar to what you're showing with the wormhole, and we see that kind of regime below a certain connectivity or a certain flow rate? So do you think that's something?
That's what I would like. This is what really I would like to have. This is really what I'm after. And they said that there was a guy called Palmer, and he's a speleologist. And he's done really interesting work, which shows also analytically that when you have these fluids, then you start, the difficulty is to make, he calls a kind of pilot tunnel, make first a very small tunnel, but then there is a balance on one side, as to say that he predicts that you have an equilibrium between the enlargement of the tunnel, but then it does not enlarge above a certain limit. So these are really these tipping points, these changes, or stable fields, which separate from another stable field, which is, I think, if we manage to define this in the modeling work, this is why modeling is useful, that we look at different scenarios, then we can see how we can translate. But these are the changes which I'm after. These, I think, that are interesting things.
Because thinking of from sort of a production perspective or reservoir engineering perspective, if you have sort of some dimensions, numbers, and you know that you're in whatever specific regime in terms of your karst formation, then you can start thinking about how you populate your reservoir models with the right karst distributions, permeability distributions, length scales, etc., and design better reservoir models.
Yeah. The problem now, we really know very, very little, because these things are mostly below seismic scale. So we don't know if these are maze-like or if they are more the branch work. So we don't have these things. We are really looking for first-order rules, This is why I also said that the 3D thing is not my biggest worry, because we really have absolutely big open questions.
If time allows, I have one more question, Sebastian.
You go ahead.
Okay, thanks very much. You're too kind today, Sebastian. So, Giovanni, you are a geologist who actually is pioneering this work of connection with numerical modelers, and as such, there are so many quantitative questions here as well. If you look into this integration of the two different disciplines, characterization and modeling and simulation, what do you think the modelers should do more that they are not doing in general to make the connection between the two fields happen better and more consistently? And what would be your advice to younger or more junior researchers in geology to do more in order to make the link between the two fields stronger than we have today?
Yeah, I have an answer for the second. For the first one is a bit more complicated. For the first one is that geologists, since the beginning of geology, their way of functioning is to increase complexity. To say, but it's more complicated. This is a typical question which a geology asks when there is a modeling study. I say, raise your hand, but this is more complicated than this. And I think the specially structured geology, we have to learn to do the opposite. We have to be able to simplify things. And this is what I was saying. If instead of populating a model with all these different sets, we populate a model with, we decide that there is a building block which is composed of 3 or 4 directions. They belong to one thing. So what I'm extrapolating is this one block here. Now, probably I will miss some other fracture, but I think it's not so bad. Probably it's not so bad. So what we have to do is geologists to put more geology in this extrapolation of these population of these models, more geomechanics, that we can simplify this. But this is something which really geologists have to work to simplify. And it's also because we don't have, especially in structural geology, we don't have really good theory ideas how to. I think it's absurd that we don't still have a theory how to predict mode 1 or mode 2 fracture. I think this is an amazing story that is there on the table since I don't know how many decades, but we're still not there yet. So there's a lot of things which you can do, but for the link with the geoengineers is really to simplify our models so that then you can make also more geology-based extrapolation rather than statistics-based or going really for the full power of putting a million fractures.
Thanks very much, very much.
I think, Giovanni, there are no further questions. So there was quite a bit of chats of technical discussions that Stefan had with some of the people, very specific details around the modeling. So Stefan, thank you for helping to answer some of
thank you very much.
Keeping an eye on the chat room. So thank you very much, Giovanni, for the presentations. Really, really interesting to see, and a big fan of trying to simplify geology again to that degree where you can make meaningful predictions.
Yeah. We would do the same advice, I guess, in simulation as well. I mean, simplification is more difficult than adding complexity.
This is
as simple as possible, but not simpler. So
precise.
I think was a right Mark Twain. He said, "Give me more time, and I write a shorter book." Shorter things, you need more time. It's much more complicated because first you have to understand, and then you can simplify. That's the problem.
Absolutely.
But I always say I don't want to leave the simplification to the modelers. I need to do it myself. That's the issue, because if I leave it to the engineers, then I don't know what's coming out.
Okay, we take it as compliment. Thank you, Sebastian. Can I close?
Yeah, you can. Thank you much.
Thank you. Thank you, everybody, for the very nice discussion, also in the text-wise as well. So I would like to take the chance to introduce the next speaker, who is also a structural geologist from University of Liverpool. We are going to host David McNamara from the University of Liverpool. David is going to give a lecture about characterizing a structural fluid flow in geothermal systems. So until next week, the same time for Central European, 3 British, 7 a.m. California, stay happy, healthy, and tuned. And we see you next week as the last live talk. And then we will receive your videos for the Christmas and end of the year. Sebastian posted all the instructions. Please go through it and send us your 10 seconds video. All the best. Thank you, Giovanni. It was a pleasure to host you today.
Thank you very much. Bye-bye.
Congratulations to